Hello students, this is Vijay Ushir. In the last lecture, we have studied about the Helmholtz function, application of Helmholtz function, that is the significance of Helmholtz function and Gibbs function, and also the entropy change in ideal gas with temperature and pressure, and also the different conditions, that is the entropy change is obtained at a constant temperature and at a constant pressure. So this we have studied in the last lecture. So in this lecture we will study the physical significance of Gibbs function. So in the last lecture we have studied the Gibbs function, that is G is equal to H minus Ts. So G is nothing but the Gibbs free energy, H is nothing but the Helmholtz enthalpy change, T is the nothing but the temperature, and S is nothing but the entropy change. So we know that G is equal to E plus PV minus Ts. By substituting the value of H is equal to E plus PV, because the enthalpy can be written as H is equal to E plus PV. Therefore, differentiating this above equation, we can get dG is equal to dE plus PdV plus VdP minus TdS minus S into dt by applying the product rule to P into V, that is P into dV plus V into dP minus T into ds minus S into dt, but at a constant temperature and pressure, that is if the pressure is constant, therefore dp and dp is equal to 0. If the temperature is constant, therefore dt is equal to 0. Therefore these two terms, that is dp and dt, vdp minus sdt, this becomes 0. Therefore the equation can be written as dg is equal to de plus pdv minus tds. This is called as equation 1. As we know that ds is equal to dq reversible upon T. That is according to Clausius equation. Change in entropy is nothing but the ratio of change in heat with respect to temperature. This is called as a Clausius equation. Therefore, we can rearrange this equation for the dq reversible. For dq reversible, we can write dq reversible is equal to T into ds. Therefore, the equation 1 becomes dg is equal to de plus pdv, and what is the value of tds? Tds is equal to minus dq reversible. This is called as equation second. So we know that according to first law of thermodynamics statement is d is equal to dq reversible minus w maximum. Therefore, for the dq reversible, what we can write? Dq reversible is equal to d plus w maximum. By multiplying the equation 2 by negative sign, so what we get? dg, this multiplying by negative sign, minus dg is equal to minus de minus pdv plus dq reversible. Therefore, we can write minus dg is equal to dq reversible minus de minus pdv. Therefore, from equation 3, what is the value of dq reversible? dq reversible is equal to de plus w maximum. Therefore, by substituting the value from equation 3, we can write minus dg is equal to de plus w maximum minus de minus p into dv. Therefore, minus dg is equal to this dE and this dE gets cancelled. Therefore, we can write minus dg is equal to W maximum minus P into dV. Therefore, we can write for the maximum work done, that is W maximum is equal to minus dg, and this minus dV gets plus PdV. Therefore, W maximum is equal to minus dg plus P into dV. Therefore, W max is nothing but the maximum work done, and PdV is nothing but the wasted work done against the confining pressure P. So here W max is the maximum work done and this PdV is the wasted work done. Therefore, the net useful work done is given by minus dg is equal to W dW useful. So this is the significance of Gibbs function, that is minus dg is equal to dw useful. Next is the Clausius inequality. So we already have studied the Clausius inequality. So consider a system in thermal and mechanical contact with its surrounding at a same temperature or at a constant temperature T. The system and surrounding are not necessarily in mechanical equilibrium. Means we have considered a system which is in thermal and mechanical contact with surrounding at a temperature T, and the system and surrounding are not necessarily in mechanical equilibrium. Therefore, the change of state accompanied by the change in entropy of system, that is ds of the system, that is change in entropy of the system, and change in entropy of surrounding, that is ds of surrounding. Therefore, because the process is might be irreversible, the total entropy will increases when the process occurs in the system. So entropy of, we know that entropy, that is the disorderness or randomness, which always increases. Therefore we can write ds system plus ds surrounding is greater than or equal to 0, that is change in entropy for the system plus surrounding, that is universe, is always greater than or equal to 0. Therefore we can write ds for the system can be greater than or equal to minus ds surrounding. Therefore, this equation implies that ds surrounding is equal to minus dq reversible upon T, where dq is nothing but the heat supplied to the system during the process. And it follows that ds surrounding is greater than or equal to minus dq reversible upon T. That is, change in entropy of the surrounding is always greater than minus dq reversible upon T. So this is the expression of Clausius inequality. So suppose the system is isolated from its surrounding. So in earlier we have considered that the system and surrounding are in mechanical equilibrium with each other. So if we now consider the system is isolated from the surrounding. So if the system is isolated from the surrounding, therefore dq is equal to 0. Therefore, the Clausius inequality implies that ds is also greater than or equal to 0. So, if the dq is equal to 0, therefore change in entropy or nothing but the disorderness or randomness in the system becomes also 0. Therefore, so this is about the entropy change. Next is nothing but the chemical potential of a pure substance. So the chemical potential of any pure substance can be written as mu is equal to dg upon dn at constant temperature and pressure. So this is the symbol for the chemical potential, that is mu, and it is the ratio of change in Gibbs free energy to the dn. dn means change in number of moles. So chemical potential is nothing but the ratio of change in Gibbs free energy to the change in number of moles, but at condition, that is the constant temperature and pressure. And the chemical potential of a substance of a perfect gas at a pressure P can be written as, for the perfect gas, mu is equal to mu 0 plus RT ln P upon P5. Therefore, we can write dg is equal to mu1 dn1 plus n1 d mu1 plus mu2 dn2 plus n2 d mu2 up to nj d mu plus mu dnj. Means for initial state, for different state, that is changing potential, changing chemical potential for one state, two state, and also changing number of moles for first state, second state. The equation for changing Gibbs free energy is written as like. Therefore we can write n1 into d mu1, this n1 into d mu1 plus n2 into d mu2 plus nj into d muj is equal to 0. Therefore, we can write in the summation form, that is summation of ni into d mu I is equal to 0. So, because ni means number of moles are constant and the chemical potential changes, therefore we can write summation of ni d mu I is nothing but equal to 0. Therefore, we can write dg upon dni, that is change in Gibbs free energy to the change in number of moles, that is dNi, at a constant temperature, pressure and number of moles are changes, that is Ni means N1, N2 up to Nj is nothing but equal to mu, that is the chemical potential. Therefore, by substituting the value of this mu1 mu into equation that is dg, so dg is equal to, what is the value of mu1, dg upon dt at a constant, dg upon dt into at a constant pressure and number of moles into dt plus dg upon dp at a constant temperature and number of moles into dp plus dg upon dn at a constant temperature and pressure into dn. So we have differentiated this equation, that is dg at a constant pressure, temperature and temperature pressure by differentiating with temperature, pressure and number of moles. That is, by first we have differentiated as dg with respect to dt by taking pressure and number of moles as a constant, and also by multiplied by dt, plus in next we have multiplied by dp at a constant temperature and number of moles. In the next we have considered dg upon dn, that is changing Gibbs free energy with respect to number of moles, and the temperature and pressure are kept constant. So this equation can be written as dg is equal to dg upon dt at a constant pressure and number of moles into dt plus dg upon dp at constant temperature and number of moles into dp plus mu1 d1 dn1 plus mu2 into dn2. So, if the temperature and pressure is constant, therefore, if the temperature and pressure is constant, therefore dt and dp becomes 0. Therefore, this equation can be written as dg is equal to mu1 dn1 plus mu2 dn2. This is called as equation 1. If the system has definite composition, that is n1, n2 up to nj, therefore G at a constant temperature, pressure and number of moles can be written as mu1 n1. If the system has definite composition, therefore this D is cancelled. Therefore we can write mu1 n1 plus mu2 n2 up to mu j nj. For 1 mole of a pure substance, we know that G is equal to mu. Therefore, we can write dG is equal to mu1 dN1 plus mu2 dN2 plus up to mu j dNj plus in the next bracket N1 d mu1. Here the number of moles are changes, that is N1, N2, N2, Nj, and here the chemical potential is changes, that is d mu1, d mu2, d mu j. Therefore, we can write dg is equal to, we know that mu1 dn1 plus mu2 dn2 up to mu j dnj is nothing but the dg. Therefore, dg is equal to dg plus n1 d mu1 plus n2 d mu2 plus up to nj d mu j. Therefore, we can write n1 d mu1 plus n2 d mu2 plus up to nj d mu j is equal to 0. Therefore, in the combined form, we can write Ni d mu I is nothing but equal to 0. So, this is nothing but the Gibbs-Duhem equation, that is change in number of moles into change in chemical potential is nothing but the 0. So, this is the Gibbs-Duhem equation. So, thank you. The next part of this we will study in the next lecture. Thank you.